the lights on my way out.
Thank you very much. Hi everyone, I'm Joe and I'm here to talk to you today about radio waves and how we use them to see into the universe before any stars existed. And to do that, I want to take you back in time, about 3.8 billion years, back when there was nothing. Nothing at all. Or more accurately than nothing, there was everything. Everything in this infinitely dense, compact ball of light and matter that contained all the information in the universe. Till all of a sudden, this infinitely dense ball started growing. And in a billionth of a trillionth of a second, this ball of light and mass that was our universe expanded 1,000,000 trillion times. In the first second of the universe, it grew from approximately a few millionths of an atom to the size of our entire galaxy. And in the first second of the universe, it had already begun to work its way into existence. In the first 20 seconds, it had created the first elements, hydrogen and helium, whirling about in this little ball, these particles that light would bounce around. And for 400,000 years, that's all the universe was. It was a bit of hydrogen, it was a bit of helium getting bigger and bigger and bigger, and light just couldn't find its way out, like rush hour on the tube. It doesn't matter how fast you are, you're not going to be able to get past all the people there. But 400,000 years after the Big Bang, that rush hour finally ended. That light got out, and we were able to see our first picture of the universe. The first picture of the universe that showed all the tiny fluctuations that happened in the first nanoseconds of its existence. The tiny fluctuations that would shape the way our universe exists today. And this is a picture that we've all seen before, or more accurately, all heard before. Because this afterglow of the Big Bang, this little picture that we have left, this cosmic microwave background radiation, it's found in the static in your TV between changing channels. It's heard in the hiss of your radio as your car can't quite find the channel. You're hearing what the Big Bang sounds like. And then, after that 400,000 years was over, nothing. No stars, nothing to see, just clouds of hydrogen and bits of helium whirling about in space, slowly getting colder and colder and colder. And these clouds would form along the pattern of this picture of the universe. The red bits where things were more dense, the blue bits where things were less dense, that hydrogen would start to follow this pattern. And as it got colder, as the universe got bigger, these clouds would get smaller and smaller and smaller, pulled in by their own force of gravitation until eventually they ignited. They ignited into the first stars, producing carbon, producing oxygen, producing iron, and for astronomers, producing light. After 1 billion years after the Big Bang was the first time we could see any new light after this Big Bang afterglow. 1 billion years afterwards. So we can see the start of the universe in the static in our TV. We can hear it in the hiss of a radio. And we can see the first stars about 1 billion years later. But what happened in between? What do we get between this cosmic microwave background and these first stars? Well, the answer quite simply is not a lot. There's not much going on. It's very hard to see. It poses a big problem for everyone around us. So what do we do? How do we work out what's going on between that year 400,000 and year 1 billion? Well, we need to look back. Look back at what there was. Look back at what we can use. And what there is those clouds of hydrogen just blowing around in the early universe, trying to find that place where they can collapse. And when we zoom in on these hydrogen clouds, we can see what hydrogen is made of. It's made of these big protons and these tiny electrons whirling about each other at massive speeds. And we can use those, because these particles have 5 properties that we care about. Each of them has a charge, a mass, a colour, a flavour, and a spin. Now the first 4, very important, but right now we don't care about them. What we care about is spin. And what spin is basically how magnets work. If you align all the spins in a piece of iron, it turns into a magnet. It allows you to pick things up. It allows you to stick things to fridges. It powers MRIs. These spins can be treated as tiny little magnets. Each individual particle with its own spin is its own little magnet. So what we can do is we can take that hydrogen whirling about in those clouds. We can take the proton, the big one, and the electron, the small one, and we can assign them a spin, and we can call those spins little magnets. And like magnets, when we put two north poles together, and we try and push these magnets together, no matter how hard we try, no matter how hard we push, they're just not going to go together. But as with magnets, when we turn one of them around and we push them together, all of a sudden, that force that was holding them apart is no longer there. And that force, that energy that was keeping them apart, shoots off a tiny packet of light into the early universe. And this is very, very useful for us, because we can find this light. We can find this light, but it's very dim, it's very small. Now, the way we measure the energy of light is based on its wavelength. If something is really, really energetic, its wavelength is really, really small, and it looks really quite blue. And the further you get, the longer your wavelength goes, the less energy this light has and the redder it looks. Now, our little packet of energy is beyond green, beyond red, beyond the visible spectrum. It goes beyond infrared and into the microwave area. Somewhere between microwaves and radio waves, we have our little packet of light. And this is great. This is useful for us, because maybe if we can find this signal, we can work out what hydrogen is doing in the early universe, that hydrogen that was the early universe. But this wavelength scale, this scale of light, has some other useful properties. It can actually let us see back in time, because after the Big Bang, the universe didn't stop expanding. It kept getting bigger and bigger. And as it got bigger, it stretched out the light itself. So the light in the early universe got stretched out more than the light in the sort of newer universe. It got redder and redder and redder. So the redder the light is, the older it is. And we can use this to work out when this light was emitted. So we can basically say, the redder something is, the older it is. The bluer it is, the newer it is. And that's great for us, because it means not only can we look back to the early universe, but we can tell when in the early universe this light was emitted. By being able to find this, we can tell lots of things. We can look back and we can see how dark matter works, how the first galaxies were flying around each other, how the first stars were born. But it's hard, because this signal we're looking for is about 10,000 times less bright than the rest of the universe around it. It's like looking for a candle in the middle of a rave, these bright lights whirling about each other, and you're looking for one tiny flame. It's right there, by the way. And we can't use normal telescopes for this, because this light is beyond what normal telescopes can see. These are radio waves that we're looking for. So what we do is, instead of getting our normal telescope with its mirrors, with its sort of various different lasers that want to point at the sky, we have this antenna that we stick in the middle of a desert, and it looks at the entire sky, from the top of the sky to the mountains on the horizon. And it turns those signals into little electronic beeps at each of the individual frequencies. And from there, we try and work out what's going on. How bright is this signal? How dim is this signal? And from that, we can work out what's going on in the universe, because we can look at each of the individual colors and see where they're going up and down. So we can look back in time and we can tell what's going on. But this is hard. It's really, really challenging, because in a rave, not only are you looking for a candle, but there are also a lot of people around dancing. And that's a problem for us. When we look back using this method, we run into a number of problems. Our telescope is an issue. Its cables, its switches, its batteries, the way its beam works, the ground plane is all a mess. We're going to throw them to one side for now. We'll call them telescope problems. Each of the individual telescopes has their problems. They do their best to mitigate for this, but it's a disaster unto itself. So what other problems do we have? Well, we have the universe fighting against us. We have galaxies shooting light at us. We have our own galaxy with dust and gas in the center of the Milky Way, emitting heat that just makes things very, very difficult. Then even the dirt on the ground around the telescope, that's reflecting light, it's emitting light. It's throwing things up into our system because we're looking at the entire sky. So even the soil underground is messing with us. And then you've got Taylor. Now Taylor's a problem because what we designed is a telescope that is very, very good at looking at radio waves, specifically at about 85 megahertz. Now the reason this is a problem is because your average radio station wants to broadcast just in this range. And what they want to broadcast is Taylor Swift's best album, Folklore. So this is an issue. They're beaming all of their light at us. They're beaming their pop music at us, and we're desperately trying to keep it out. So how do we keep it out? Well, we put our telescope in the middle of a set of mountains. We desperately try and build up barriers so we can stop pop music coming in, and then the mountains themselves become a problem. Because these mountains start emitting light, they start reflecting light. It's a whole mess. So how do we deal with it? How do we get around it? How do we fight these issues? Well, there are a load of teams who are trying. There's the team who work with Cambridge and in South Africa in the top left. Now they put their telescope in the middle of a desert surrounded by mountains. They said, you know what, we don't want to deal with any radios coming in. We're just going to stick our thing here and hope for the best. Then you've got the team from Arizona who said, actually, we're fine with radio waves coming in, but the mountains themselves, they're too hard to deal with. We'll take the open air and hope that we can sort things out. Then you've got the team from India down here who said, you know what? Frankly, we don't like soil. We're going to build the thing in the middle of a lake. We're going to hope that radio waves don't come in from the cities nearby. And fingers crossed that'll work. And then you've got this team over here. This is the MIST team. Now what they did was they said, we don't want to deal with the same kinds of soil. What we want to do is we want to take our telescope and be able to move it across the world so we can mitigate for any issues of the soil coming in, because there'll be so many different kinds, it'll all counter each other. Now this was genius. Whether it's genius science or a very, very genius way of getting good holidays from your university, we're not quite sure yet, but genius nevertheless. So let's talk about the Arizona one first. Because they were the first ones to really put their thing into action. They said, we don't want to deal with mountains at all. We'll look and we'll look and we'll find something. And find something they did. Now, forewarning, this is the only graph in this. We won't deal with any more. But for now, we'll just have a quick look. So they found this black dotted line here, this signal detected by edges. Now this is a weird black dotted line, because if you look, it's very, very different to all of the nice coloured lines earlier. The coloured lines are what the theorists said should be there. And the black dotted line was what the team from Arizona found. Now it's about twice as deep as anything that could have been predicted. And it's also a very different shape. Instead of being a nice curve, it's a weird upside down top hat. And that threw people. So people tried to work out what was happening, what was going on. First, experimentalists came along and they said, well, have you checked all your cables are in the right place? Have you checked the way you've done your data analysis is right? And there were some arguments back and forth, and that never really got resolved. But theorists came in and they said, well, what if this isn't an experimental thing? What if this is new science that we've never seen before? What if this is cosmic rays beaming in from the early universe? What if this is some kind of electric dark matter? What if this is galaxies in the early universe shooting light at us more powerfully than we could expect? What if this is quark axion nugget dark matter thermal emission from the early universe? Now, I don't know what that is. I've asked around. No one seems to know. My pet theory is that it's a cry from help. The theorists have been like, guys, we need more stuff here. Please, for the love of God. So more stuff came along. And it was the team from India this time. The team that said, you know what, we're not going to deal with soil. We're not going to deal with ground planes. We're not going to deal with dirt. And in fact, the way they built their little telescope as this cone meant they didn't have to deal with the antenna doing weird things when it's shooting off its beam. And they looked, and they looked, and they looked for this signal that the team from Arizona had found, and they found nothing. Now, when I say they found nothing, it's not to say that this nothing is useless. What I mean is that they so very, very precisely found nothing that it really irritated the people from Arizona. They found nothing to the point where they had to turn around to that team and say, look guys, we don't believe you found anything either. So they argued back and forth a lot, and more theorists jumped in and more data people jumped in, and they tried to argue it out. But eventually we decided, okay, more data is needed. And that's where the team from Cambridge come along. And they said, you know what? All of this is a problem. The whole thing's a mess. So what they did instead was, instead of trying to mitigate for these problems, trying to say, okay, we're going to build it in a way where we don't need soil, where we don't need mountains, where we don't need beams, where we don't need cables. They said, what we're going to try and do is model it. So instead of building it, they got a team of data analysts, and they put them in a room for about 5 years. They locked the door. They opened the door 5 years later, which is roughly now. And they said, right, guys, we hope you found all the problems, all the issues. Now we're going to turn this thing on, and you're going to look at space. And that's what they did. And very recently, this telescope was first turned on, and it started looking at space. Now, this might not look like much, and it might not be much, but this is the first little light that we got of the early universe. Those little spikes are Taylor Swift doing her thing. Those downward little blobs are something else that we haven't quite worked out yet. But somewhere in there is our signal from 12 billion years ago, and we just need to find it. And if we do find it, then just maybe we'll be able to learn about dark matter. Just maybe we'll be able to learn about the first galaxies and the first stars. Maybe we'll be able to learn about how everything came to be, if only we can just about find those candles. They're just there, by the way. Fantastic. And that's everything from me. So thank you so much for listening. I hope you enjoyed, and if you have any questions at all, please feel very free to ask. Also, I have no idea how to turn the lights on, so we're stuck like this for a little bit. Absolutely.
Why didn't they build a radio telescope in space?
It's very hard to send things into space. It's very expensive to send things into space. What people want to do is they want to build a radio telescope on the moon. Because in space, you don't have to deal with some of the problems you have to deal with on Earth. The atmosphere is an issue. You have to deal with, obviously, radio waves coming in. On the dark side of the moon, however, you can block all of that out. The problem is getting things to the dark side of the moon is very challenging and very expensive. And trying to tell someone, look, right, we're going to build a rocket ship. We're going to stick like a little metal bit on it. We're going to send it to space so we can look back 12 billion years, and people will be like, where's the money in that? And we'll be like, we don't know. So there are absolutely people trying to do that, and it's a very, very good idea, but challenging to do, unfortunately.
Before there's any more questions, I'm going to be the bearer of bad news, I'm afraid. We were setting up telescopes outside, and then the clouds have come over like a roof, and there's nothing. So after these questions, we're going to go for tea and biscuits, then there'll be a planetarium showing here. So yeah, I'm really sorry. We were all keenly setting up, and then the quote was, it was like the Wimbledon roof closing, and just clouds came over. So yeah, which means we could relax and ask our speaker some more questions with the aid of this fancy throwable microphone. So that's a bonus for anyone that wants to ask a question. Okay. Any more questions for our speaker?
Absolutely.
Microphone?
No, I'm fine. So when the hydrogen collapses,
Yeah.
and it ignites, what is the source of ignition?
So as the hydrogen sort of gets closer and closer together, it's pulled in by gravity. And eventually that pull is so strong that these hydrogen atoms smash together. And when they smash together, they form helium. And helium is weirdly, so helium is made out of sort of a number of things, but it's 2 protons and 2 neutrons. So when you smash protons together, you get sort of a proton and neutron, you get more things flying in, it makes more things. But the answer is helium, as it's 4 different things, is very, very slightly lighter than 4 different bits of hydrogen. And if we use Einstein's big equation, E equals mc squared, if you have a little bit of mass left over, you get a lot of energy. So as soon as you lose that bit of mass, as you put your hydrogens together and make helium, that little bit of mass left over that sort of should be there is turned into energy. And that's what ignites. That's what powers our sun. That's what powers all the stars there is. It's that fusion. But yeah. Absolutely.
So the radio telescopes you showed us a very specialised piece of equipment.
Yeah.
What's the reason why you can't use some of the other big radio telescopes that are already in place around the world?
So it varies what we're looking for specifically, because there are lots of different ways you can do this. A lot of them are quite directional. They want to look at sort of one point and say, okay, what's going on over there? They might be looking for stars wibbling about in a weird way. They might be looking for sort of weird earthquakes on neutron stars, something like that. But because our signal is so dim, we want to look at the entirety of space and try and pick it out from there. If we're just looking at one place, it's going to be very, very, very challenging to find it. Fantastic. Do you have a question?
I just didn't quite understand one thing when you were talking about what makes the different things magnetic. What was it? You said something about it's spinning. I just didn't quite understand that.
Yeah, so when we talk about sort of properties of particles, there are 5 that we consider. There is charge, mass, color, flavor, and spin. Spin, don't think about it necessarily as something spinning around. It's a weird quantum property that just exists. It's basically telling you which way your atom is pointing. Is it pointing up? Is it pointing down? And based on the way it's pointing and how that interacts with your charge, it basically functions as a magnet. So if this is pointing up and charged one way, and this is pointing up and charged one way, they don't want to go together. But if you flip one over, they just about have room. Perfect.
Can I ask you a question, but can I request that someone through that microphone?
Oh, sure.
Absolutely.
Catch.
Oh yeah. You mentioned that the latest thing that happened was that someone ended up modeling a telescope and from like a data set and got that graph that you showed us last. How did they get the data set if everyone agreed that they had to find more data?
So all of these sort of things that so those 3 things that I've shown you, those are people who have data. Now, the last one I showed you with that last little graph that's sort of the Cambridge's team first look at this stuff. They've been sort of sitting around and trying to work out how this telescope might look at space. And when we sort of try and work out how it might look at space, we also throw in all the issues that we think there might be there and then try and account for it. So for the last 5 years, it's been a lot of people doing data analysis on data that they made up. And then now, once they've sort of tried to work out where all the problems might come in, when we look at real data, they're going to be able to understand that. But the graph you saw was sort of the first look that that team has had at space through that telescope. Fantastic.
Any more questions? It's good to know. Okay, in that case it's time for a tea break, which will be followed by a planetarium show back in here. Can we thank our speaker again, please? Bravo, very good. Thank you. That was excellent. Are you happy?
Yes.